Howdy y'all, this is just a video, probably going to be 15-20 minutes, so if you want to break it up, that's fine. I'm going to get to kind of the finer points of this chapter and the next. Reminder that we do not have class on the first week of April, so this will be basically what you want to do with your ed puzzles and your smart book and whatnot. So I'm going to not cover obviously all of these slides. There's a lot for this chapter, but I'm going to focus on the fundamentals, so then you can go on to other things. So first thing with glaciers, important to know because you're going to probably see this again, is that they are part of both the water and the rock cycle. And basically we're going to kind of understand kind of how they're formed, how they move, and their importance to the ecosystem. So the first thing is you need to know kind of what the different types are. And so one of them is called an alpine glacier. I guess it's more commonly now also called a valley glacier, but it was called alpine when I learned it. And this forms in mountainous areas, and you can pretty much get the idea of what's happening here, where you would have massive amounts of snow falling between mountainous areas, creating this gigantic valley of huge amounts of snow that then kind of form and can even move as a unit further down a hill or the mountain. And so that's one particular type. And obviously the ice sheets, which are gigantic continental size, or at least they used to be before global warming. These cover massive areas of land and have for a very long time. And this is a lot of the fear we have with some global warming, is that some of these things are super old. And as they melt, obviously they are going to cause a lot of problems, and we'll get to some of them later. But they're way bigger. And if you take a look at the world map, you'll see that there are some areas of the planet that still have snow on them almost all the time. Chances are they would be part of some degree of a continental glacier. So basically kind of how they move. This slide and the next one kind of just give you a general idea. This word is actually pronounced crevasse. It could also be called crevices. But you can see here they kind of shear off and can create these crevices or areas of stress between them. And then what you end up getting would be something like this. You can see the crevasse here typically at the front of the glacier. And obviously the reason this thing's moving is because of gravity. Which makes sense. So headed, of course, downhill and eventually probably towards some sort of water source. But the accumulation, this is kind of how they start. Obviously, higher elevations, you're going to have more precipitation, more snow, and it's going to stay colder longer to say snow and not turn into rain. And then, of course, gravity is going to take over and start pulling this thing downhill. And then what you kind of get almost is like an underpinning. And that's why it looks a lot like crevasses. And from there, you also, because of friction and the temperature is typically a little bit warmer, you're going to have some little teeny streams called braided streams that are flowing. Usually a lot of that's from the underside of the glacier. And of course, the wastage area is where you're going to get a mixture of stuff. So it's a very homogeneous area of the glacier near the zone of wastage. And also don't forget, this thing's going to act like sandpaper. As it goes, and most move very slow, like, meters a year or meters a week, sometimes centimeters a week, depending on a lot of different things. But they're going to pick up a lot of the rocks. They're also going to shear off a lot of the surface, which explains a lot of the Midwestern United States and how flat that is. It was basically caused by glaciers moving from north to south long time ago. So this is one of the pictures of the fears that we have. There's a video called An Inconvenient Truth. It's a documentary done by Al Gore, probably around 2000 or so. You may want to watch it. But this is the kind of what we have going on now that's a concern, is that if you take a look at this area in 1935, snow covers hundreds and hundreds of miles. And so what that's going to do is as the sun hits that ice, it's going to radiate back up into the atmosphere. But now that the glaciers are melting, that solar energy is going to be caught in the water. And water is very good at holding energy once it gets it. And that's going to perpetuate warmer temperatures as well. And that's kind of where we're in a bit of a pickle. So to just kind of give you an idea about why we care so much about them, besides the fact that they hold massive amounts of fresh water. And the fact that they do hold fresh water, the other problem we now have is since these glaciers are all fresh water, and they are literally dumping millions and millions of gallons of snow that's melted is now water into the ocean, it is starting to desalinate the ocean just a tad, which is kind of not a big, I'm kind of a very big deal as well. I'm not going to go over all of these landforms. You just look them up. It's straightforward. This is more like declarative knowledge. So you definitely want to pay attention to what landforms are created when glaciers do erode. In addition, while you're studying, you want to pay attention to this slide as well, which kind of gives you an idea about the landforms that glaciers make as they deposit certain things. And so those two things would be valuable to look at, hint, hint, as you are studying. So kind of a little bit more on how they move and why they move. You can see here that if the ground under a glacier is not flat, this will tend to kind of lock a glacier in, and would basically stay there for a long period of time until enough, sediment of snow, whatnot. I shouldn't say sediment. Enough snowpack would cause some damage in the bottom. But otherwise, if you have an area that's smoother like this, the actual glaciers can slide, and they kind of head towards, again, like I said, the water, where you get the term iceberg from. And so here's a glacier now reaching the sea, and obviously what happens all of a sudden, the reason it creates icebergs and breaks is because there's nothing under it. So as it keeps being pushed down towards the water, this area of massive land right here doesn't have anything under it. And that is going to cause obviously some degree of stress, and it can break the glacier into icebergs, some of which can be the size of Delaware and larger. We're not talking about little pieces of ice here. I mean, they could be little ones as well, but they can be very, very, very large. And they're sometimes also referred to as ice sheets. This is a cool picture from the chapter. It kind of gives you a really good topical view of some of the evidence for the fact that glaciers were in the Midwest and did travel south. You can see here the topographical area or map here of these moraines caused obviously by a glacier over time, and you can see how smooth this area is, yet it's surrounded by rough areas like way up here and way down here. And so this whole area being really flat is a generalized indication, as well as the sediment. If you can track the sediment all the way down pretty much to Louisiana, or as how they like to say down there, Louisiana. And this kind of gives us just again more evidence of the direction that the glaciers used to take when they covered that part of North America. This chapter does have a fairly stark kind of abrupt change in talking about glaciers, moving on to a little bit of the tilt of the earth, and I'll cover that in another chapter with seasons and whatnot. But we can see here that there is some discussion of tides, obviously in relation to glaciers and shorelines and whatnot. So you do have to have a fundamental understanding of what causes things like low tide, and as you guessed it, the moon has a lot to do with it, and that has basically to do with gravity. And gravity is a very interesting thing to talk about because nobody really knows what it is except we know the effect of it. And basically everything has gravity, and everything is pulling towards everything else. And that's a whole other class that I'm not going to necessarily get into now. But we pull on the moon pulls on us. And so depending on where the moon is in relation to certain aspects of the Earth, the moon can have a stronger pull or a weaker pull. And if you take a look, for example, right here, that as the Earth is rotating this way, and the moon's gravity right here you have this mound of water, this massive, gigantic mound of water that's being pulled by the moon because it's closest to the moon. And so what does that do? Well, it thins out the water to a degree on the sides because it's being pulled towards moon's gravity. And since we are rotating once a day, that's basically why, because where we stand is going to go through those mounds once a day. And so you're going to get the high tide and the low tide. And so you can also see here that why are some tides stronger than other tides? That again has a lot to do with relative distance and whatnot. Let me move on to two other things. So for any of you like fellow surfers out there, you may find this of interest, but what determines when a wave actually breaks? And a lot of it has to do with what's going on under the water. Actually, most of it does. And of course, whatever kind of swell or current you have. But basically, you can see here that a wavelength, even whether this is in physics, talking about sound, or whether you're talking about actual waves, a wavelength is designated as the difference between the distance of two waves at their highest point. So that's called a wavelength. And in terms of the area when a wave would break on shore, that usually happens where the wave base, which is here, it's going to break where the wave base is half of the wavelength. So basically from here to there, once that distance hits on the wave base, that's when the wave will actually break. And so it obviously depends on a lot of factors, but obviously what's going to bring large waves is the larger swells from the outside. But that's what determines where they break and when they do, based on that particular size. So this is unfortunately an all too common picture. You guys probably weren't even alive when this was happening, but you can see here on the left that you have all these houses here. This was very common back then, literally right in the water. And then all of a sudden, after one storm, you have this. That's going to keep happening, and we're going to talk about that when we talk about hurricanes and weather in a few weeks. But what are some ways we can fix that? Because I do know that there'd be a question about that. And so here's one particular scenario. Actually really three that we can use, and we do use, to kind of slow this down. So you can see here things like jetties, which is just dumping a whole bunch of rocks. If ever you guys go to Lewis Ferry, they created jetties out there, which breaks up the current and also breaks up the wave strength big time. And jetties, by the way, jut out into the water, whereas seawalls are against the water. And so I'm sure your areas are familiar with areas like that. And so this is one that would be both. And if you take a look here, you can even see the wave activity out in the ocean is pretty significant, and there's almost none on the shore. And those are just some of the things we can do, obviously, besides also pumping the beach back up from erosion from storms, which we talked about a few weeks ago. The last part of this chapter I want to talk about is what's the basic difference in the way that erosion and coastal hazards can be be caused, especially by water erosion. So we can see here we have two particular different scenarios. One's called an overwash regime and one's called an inundation. And this is almost like sometimes, by the way, like a before and after, but doesn't necessarily have to be. So an overwash, you can see here, is where there's some kind of barrier that's protecting, especially the angle. You can see the angle of the beach, that's protecting the land. And there's the lowest and highest point at this left trough here, and that has to do with what's called the overwash regime. So it's the height of the waves that reach the top of this area. Then what you do is you end up pushing all of the sediment towards the beach. So you can see how there's this thing right here, but in this picture it's gone, and that's because it's moved to the right. And from that point now you have a basic inundation zone. So to show you a picture in that real, we're looking at something like this. So you can see here that we have an inundation, that this area probably had some sort of seawall, or hopefully it did, or maybe not. And it's for whatever time, you can see that this must have been high enough that people figured, oh, that's fine. It's going to act like a barrier. But then what happens is a big storm or many storms just ripped away the beach, and now there's no height, and it's gone. And so that's kind of what happened to Rehoboth last year in the fall. And we had that nor'easter that in 3 days took the beach that looked like this, and then it now looks like this. And so you can see here, obviously erosion of dunes is a big problem, and dunes serve the purpose of providing some kind of barrier, obviously. And so that's just what I wanted to touch on, the finer points of this chapter. So now I'm going to hit on 12 a little bit. And this is actually the chapter 12 PowerPoint from the previous version of a different book, and I like it. And it also covers everything you need to know from yours as well. So if you see a couple little pictures referring to like chapter 9 or something of this, don't worry about that. This is actually chapter 12, the water cycle, or hydrologic. So that should help as we go down. So basically, again, the idea of this whole chapter is related to the earth and its relationship with water and its water supply. So there's a couple different processes involved with the water cycle, things you definitely want to pay attention to. And one of those obviously is precipitation, knowing the difference between a couple words like, what's precipitation? Basically rain or snow. And evaporation, how that water, returns from a body of water back to the atmosphere. Infiltration, how water infiltrates certain areas to create things like caves and sinkholes, etc. Runoff, which we obviously have a problem here in Sussex County with that, from all the chemicals in the fields running off and the amount of nitrogen into areas they shouldn't be, and whatnot. So that's kind of where we're going to be going with this chapter. So this is probably something you learned back in about 7th grade, maybe high school if you took it or not, but it is important, obviously, that you understand this system. There really is it's a cycle, and anytime something's a cycle, that doesn't mean that there's necessarily a start to it. So we can really start anywhere. And I think for our purposes, let's just start here in the body of water like the ocean. So, where we have evaporation, and obviously the warmer the water, the more evaporation we have, and that's typically why we have hurricanes in, anywhere from like normally August to like November. That's not, random. That's because the water is the warmest off the west coast of Africa at that particular point. So what happens? So we have evaporation, and that evaporation obviously normally is going to be carried in some kind of cloud, because as you get up higher, the temperature gets cooler. So the water condenses in the form of a cloud. And that cloud, as you know, doesn't sit there. It's moving, obviously based on a lot of different things, wind currents and whatnot. And then at some point, those clouds get so full that they then drop whatever they have as precipitation somewhere. And that precipitation then is going to infiltrate to the lowest possible point, which might be in a stream, which might be in an aquifer, which is an area of water that's under the ground. It might be going down a river back to the water, and then it basically, from that point, just repeats. So one particular slide I kind of liked, really for those of you who don't understand why some river rocks are smooth, here's why they are. And you can see here that, depending on the size of the sediment, the lighter the mass of the sediment, the more it's going to be carried in the actual water itself. And it can be something that you see, like a suspended load, or it can be dissolved, something you don't see, and that's carried in the water itself. And then obviously as the pieces of sediment are larger, therefore have more mass, they tend to be near the bottom. And then you finally get the largest rocks that just kind of roll. They literally slide and roll along the bottom. And that's why they're usually never perfect circles. They're usually kind of flat. Almost like, a flat tire in essence, and that's because they slide a lot as well. But the rolling is what causes them to kind of erode based on, they're scratching against the ground, and that's why a lot of river rocks are the way they are. So a couple terms that'll help are these, and kind of knowing what these are. And the first one, actually, and the last one kind of makes sense with their names. So bedrock channels are obviously channels that have been cut into the actual rock itself, almost like if you want to think like the Grand Canyon. And then alluvial channels are kind of loose, like the things that you would see at the bottom of a mountain, where pieces of rock are constantly falling down at the base of it, and those are very loose. And then obviously meandering means exactly what it says, is that these have a lot of bends to it. They're not straight. And of course, the last is called a braided stream, and I'll show you a picture of that. So that's a braided stream, which makes a lot of sense. It looks like a braid. And that, of course, is just another way that valleys can be shaped through the movement of water. So how a floodplain can be created would make sense. If you look at this first picture, what you notice, by the way, is it's very high. It has a very varied elevation. And that water is probably moving pretty darn fast. And what it's doing, by the way, is it's pulling with it, because of the speed of the water and how small the area is, all kinds of sediment. And over time, you're going to have this area kind of carved out. The water's going to slow down some. And as it slows down, it's going to not only erode away at its walls, it's also going to deposit some of the sediment that was from the more northern parts of it. And you end up getting something like this, and you can see this is a meandering body of water. Out of all the pictures here, I think this would be most poignant for those of you like me that live in Sussex County. This has to do with water and the water table in relationship to, for us, it would be a well, and what the aquifer is. So you can see here that The water table is basically the level at which there's water underground from all kinds of previous precipitation. And it doesn't mean it's a lake. A lot of people have this idea that the aquifer, when you have your well, that there's just this cave and it's a massive swimming pool and we just suck water out of it. That's not the case. It's basically like this. It's rock that has a lot of water in it. And so what we need to do, and we're doing less of it, which is good. I mean, I have a well in my front yard, is that they basically have to drill down until they hope they hit something like this. An aquitard is a mini, for lack of a better word, aquifer. And it's usually well above the main water table. And of course, the closer you get to the ocean, the water table is higher and higher and higher. And you can see an unsuccessful well would be driven here because it just didn't happen to be hitting any water. So if somebody's well dries up, the company has to come back and basically go deeper. But you can see the difference between these two here. There's an exam or question or two about this picture, especially the one to the right. But you can kind of see here, it explains how they're created and how sediment is deposited. So if we talk about, let's just move to the meandering. As this water comes around the corner in a circle, the water on the outside is moving the fastest. And that's because it's making the largest, it's covering the largest amount of area to get to the end. And that's why, the example of the equator, people moving on the equator, they're moving faster because it's a larger circle they have to make than people living at the North or the South Pole. So this travel distance here on the outside, that water is moving faster. So the water on the inside doesn't have to travel as far. The circle's smaller, meaning if I took a piece of string right here and I put the string from the top to the bottom right there, and then took another piece of string on the inside and measured it from the same top place to the same bottom place, it means a string on the outside is going to be longer. But the water has to basically get to the other area at the same time. So how does it do that? It travels faster. And that's why the water on the outside is faster, and therefore that's why the deposits of sediment happen on the slower areas, which is the inside, the areas where the water doesn't have to travel as much. And so that kind of makes the same kind of sense in this particular thing. The water here is moving faster, like on the outside, than the water on the inside. That's why the deposit happens here. So putting it all together, our last slide, how does it relate also to deposition and erosion? And you can see here, if we got this particular area, this fast water on the outside, because it's moving so fast, it has more force. It's going to be eroding away at the bank, the backside of this thing a lot. And then as it travels, you notice what's happening here. It's going to kind of run into this bank, and this is slower moving water right here, and that's why it's going to deposit it at that particular point. That's over time going to exacerbate this curve into a meandering stream, and that happens over a long kind of looking something like this. So this is really cool. It's actually a satellite image right here of this stream, and you can see the crazy meandering that happens, and that's because of that combination you can see here of massive erosion and then depositing it again, massive erosion, depositing it again. And so hope that helped to give you a little background of these two chapters, and I will see you in a little bit.